Gravity is the fundamental force that drives galaxy formation. It's the attractive force between all matter in the universe that pulls objects together. From planetary orbits to the largest cosmic structures, gravity shapes everything we see in space. Without gravity, the matter in the universe would remain diffuse and galaxies would never form. Gravity pulls gas, dust, and dark matter together. Dark matter provides the gravitational scaffolding for galaxies to form. Computer simulations help us understand how gravity brings together different components of the universe over billions of years. The end result is the beautiful spiral and elliptical galaxies we observe today, their structure maintained by gravity's constant pull. In summary, gravity is the primary architect of cosmic structure. It pulls matter together across vast distances, creates the cosmic web of filaments, enables gas to collapse into galaxies, and maintains these structures over billions of years. This fundamental force sets the stage for the complex process of galaxy formation that we'll explore further. The primordial universe began with remarkable uniformity, but contained within it were the seeds of all cosmic structure we see today. This funnel shape represents the evolution of our universe. At the very bottom, in the quantum geometry region, tiny quantum fluctuations emerged during the earliest moments after the Big Bang. During the inflation period, quantum fluctuations created tiny variations in the density of matter and energy. Gravity played a crucial role in amplifying these initial density differences. Slightly denser regions exerted a stronger gravitational pull on nearby matter. Over time, this gravitational attraction caused the denser regions to accumulate even more matter, while less dense regions became emptier. These amplified density variations eventually grew into the vast cosmic web structure we observe today. In this simulation, we can see how matter has collected along filaments and nodes, with denser regions shown in red and less dense regions in blue and purple. These same principles of gravitational attraction led to the formation of individual solar systems, including our own. To summarize, galaxy formation begins with quantum fluctuations that created tiny density variations in the early universe. Gravity amplified these differences over billions of years, resulting in the complex cosmic structures we observe today. In the vast regions of space, massive clouds of hydrogen and helium gas begin to collapse under their own weight. As gravity pulls matter together in denser regions, it creates a fundamental process in galaxy formation. The gravitational force pulls gas inward from all directions, initiating collapse of the cloud. When a gas cloud collapses, potential energy is converted to heat, causing the temperature to rise dramatically. This increase in temperature, combined with the uneven distribution of matter, causes the cloud to fragment into smaller, denser regions. Each of these fragments can continue to collapse and eventually form individual stars and star clusters. The collapse of gas clouds is governed by a delicate balance of opposing forces. Gravity continuously pulls matter inward, causing contraction and heating of the gas. As the gas heats up, it creates an outward pressure that counteracts gravity. The interplay between these forces determines how rapidly the cloud collapses and fragments. This gravitational collapse is a critical step in galaxy formation, setting the stage for the emergence of stars and eventually complete galactic structures. Angular momentum plays a crucial role in shaping galaxies during their formation. As clouds of gas collapse under gravity's pull, any slight initial rotation becomes amplified. This process is similar to an ice skater spinning on ice. When they pull in their arms, they spin faster. This is due to the conservation of angular momentum. As the mass moves closer to the axis of rotation, the rotation speed increases. This conservation of angular momentum explains why many galaxies form disk shapes with distinctive spiral arms. As the cloud collapses, it naturally forms a rotating disk because angular momentum prevents material from falling directly into the center. Within a galaxy, stars orbit the galactic center at different speeds depending on their distance from the center. Stars closer to the center complete their orbits more quickly than those at the outer edges, creating a differential rotation pattern. Gravity plays a crucial role in maintaining the galaxy's structure over billions of years. It balances the rotational forces that would otherwise cause the galaxy to fly apart, keeping stars in their orbits around the galactic center. At the heart of most galaxies lies an extraordinary phenomenon, a supermassive black hole. These cosmic giants form when gravity concentrates enormous amounts of matter in galactic centers. Several theories explain how these giants form. They may begin as smaller black holes from collapsed stars that grow over time, or form directly from the collapse of massive gas clouds in the early universe. These giants are truly massive, weighing millions or billions of times more than our Sun. Their immense gravitational pull affects everything around them, from stars to gas clouds. The intense gravitational forces they exert can accelerate matter to near light speed, creating brilliant accretion disks of superheated gas. We can observe the effects of these cosmic behemoths by tracking stars that orbit around them. In our own Milky Way, stars circle the central black hole at tremendous speeds. One of the most intriguing discoveries is the relationship between a galaxy's mass and the mass of its central black hole. The larger the galaxy, the more massive its central black hole. This suggests they co-evolve, with gravity mediating this remarkable relationship. This coevolution occurs through feedback processes. Black holes influence galaxy formation by releasing energy as they consume matter, while galaxies supply the material that feeds black hole growth. In conclusion, supermassive black holes are not just passive residents of galactic centers. They actively shape their host galaxies through gravitational and energetic processes. This relationship demonstrates gravity's fundamental role, not just in forming these cosmic giants, but in guiding the entire evolutionary path of galaxies themselves. Galaxy mergers and interactions are among the most dramatic events in our universe. When galaxies pass near each other, their mutual gravitational attraction creates powerful forces. These gravitational interactions can have several effects on galaxies. First, they can distort galaxy shapes, creating tidal tails and bridges. This is clearly visible in the mice galaxies, where we can see dramatic tidal tails forming as the galaxies interact. Second, these interactions compress gas clouds, triggering bursts of new star formation. And finally, galaxies can completely merge, combining their stars, gas, and dark matter. A galaxy merger unfolds over hundreds of millions of years. This sequence shows the progressive stages of two spiral galaxies colliding and eventually forming a single galaxy. These gravitational interactions explain the diverse shapes of galaxies we observe in the universe. When spiral galaxies merge, they can transform into luminous infrared galaxies, then ultraluminous infrared galaxies, and eventually elliptical galaxies or quasars. The outcome of a merger depends on the galaxies involved. Two spirals typically form an elliptical galaxy. Minor interactions can create irregular galaxy shapes with unique features. And multiple mergers over time can create giant elliptical galaxies found at the centers of galaxy clusters. Mergers are essential to galaxy growth. Our own Milky Way has grown by consuming smaller satellite galaxies. The Milky Way is still growing today, absorbing smaller dwarf galaxies, and in the distant future, it will collide with our neighboring Andromeda galaxy. Modern telescopes like Hubble and James Webb allow us to observe galaxies at various stages of interaction and merger. By studying these galactic collisions, astronomers gain insights into galaxy formation history, star formation processes, and the growth of supermassive black holes. Within galaxies, gravity plays a crucial role in the formation of stars. The process begins with vast molecular clouds of gas and dust. Gravity pulls these molecular clouds together, causing regions of higher density to collapse inward. Star formation depends on a delicate balance of forces. While gravity pulls material inward, several opposing forces resist this collapse. The outcome of gravitational collapse depends on the initial mass of the cloud. Smaller collapsing clouds form smaller stars that eventually become white dwarfs. Massive clouds form large stars that end their lives as supernovae, leaving behind neutron stars or black holes. Within a galaxy, star formation is not uniform. It primarily occurs in regions where gas is abundant, like the spiral arms of disk galaxies. The galactic structure we observe is largely shaped by where and how stars form under the influence of gravity. Stellar nurseries are the birthplaces of stars. In these regions, many stars can form simultaneously from the same collapsing molecular cloud. The beautiful nebulae we observe are often these stellar birthplaces, illuminated by the young stars forming within them. Star formation is an ongoing process throughout a galaxy's lifetime. As gas clouds collapse to form new stars, the appearance and structure of the galaxy gradually evolves. Different rates of star formation create the diverse galaxy types we observe in the universe. Star formation is a self-regulating process. When new stars form, they release energy that can disrupt nearby gas clouds, temporarily halting additional star formation in that region. This feedback creates the complex patterns of stellar distribution we observe in galaxies. Gravity is the fundamental force that maintains the distinctive structures we observe in galaxies. The diverse structures we see in Edwin Hubble's galaxy classification system are all maintained by gravitational interactions. One of the most striking features of many galaxies are spiral arms, maintained by gravitational density waves. These spiral arms aren't fixed structures, but rather waves of compression. As gas clouds orbit the galaxy, they're compressed when passing through these gravitational density waves. This compression triggers star formation, resulting in the birth of bright, massive stars that highlight the spiral pattern. These massive stars burn quickly and die out, which is why we primarily see young stars in spiral arms. Central bulges are another key structure maintained by gravity in many galaxies. Bulges form as gravity pulls stars toward the galactic center over time. There are three main formation mechanisms for these structures. First, the rapid collapse of primordial gas clouds under gravity can form a large bulge of ancient stars. Second, environmental effects like galaxy interactions can cause smaller galaxies to fall into disk galaxies, inflating the bulge. Finally, internal evolution through bar structures can shovel gas to the center, creating new stars and growing the bulge over time. Many spiral galaxies also contain bar structures, another fascinating feature maintained by gravity. Bars form when gravitational instabilities in the disk create elongated structures of stars that rotate as rigid bodies. These bars act as gravitational channels, funneling gas inward toward the galactic center, which can fuel star formation and feed the central black hole. The inflowing gas can form nuclear rings and even secondary bar structures, as shown in this image. Over billions of years, these bar structures may evolve and eventually dissipate as the galaxy continues to evolve. We can measure how gravity has shaped galactic structures by examining surface brightness profiles. This graph shows how surface brightness decreases with distance from the galactic center. Gravity pulls more stars toward the center, creating a higher stellar density and therefore greater brightness. Different structural components create distinctive profiles in these measurements. Bulges typically show a steep exponential decline in surface brightness, while disks display a more gradual exponential decline. The structures we see today resulted from gravity's influence throughout the history of galaxy formation. There are two primary theories about how gravity assembled galactic structures over cosmic time. The inside-out theory suggests that galaxies form as smaller protogalaxies merge together under gravity, gradually building larger structures. The outside-in theory proposes that formation begins with a central black hole, with structures developing outward from the gravitational influence of this central mass. Gravity will continue to shape the evolution of galaxies far into the future. Our Milky Way is on a collision course with the Andromeda Galaxy, drawn together by their mutual gravitational attraction. These two massive spiral galaxies are being pulled toward each other by gravity, a force that will eventually bring them together in about 4.5 billion years. The collision will unfold over billions of years, completely transforming both galaxies. On a much larger scale, gravity has created an immense cosmic web of galaxies and dark matter. However, a mysterious force called dark energy appears to be counteracting gravity's pull throughout the universe. This creates a cosmic tug-of-war. Gravity pulls matter together while dark energy pushes space itself apart. Gravity's effects extend beyond just pulling galaxies together. It can even bend the path of light itself. The battle between gravity and dark energy will determine the ultimate fate of our universe. If dark energy continues to dominate, the universe may expand forever, leading to a big freeze. But if gravity eventually overcomes dark energy, we could see a big crunch where everything collapses back together. This cosmic tug-of-war between gravity and dark energy will ultimately determine the fate of galaxies and the universe itself.